Friends, today we will continue our study on small signal stability of a single machine in finite bus system. In the previous lecture, we have studied the effect of automatic voltage regulator on the damping and synchronizing torque coefficients. We have seen that in case the operating condition is such that the constant K phi is negative, and if we increase the AVR gain, then we find actually that the damping torque coefficient becomes negative, while the synchronizing torque coefficient is positive. It means we have a very conflicting type of effect on the damping and synchronizing torque coefficients when the AVR is considered. Okay. That is, now we have also computed through a simple example that if we increase the AVR gain, right, then the damping torque coefficient becomes more and more negative. Now, to illustrate this thing further, for a typical problem, we have computed the K1, K6 constants over a wide range of operating condition, and we will just examine how these constants vary as the system loading varies. In this figure, we have plotted the variation of constant K1 as a function of real power output P for 3 different values of reactive power output. That is, this graph shows the variation of K1 for Q equal to 0, that is the reactive power output of the generator is 0, and we are varying the real power only. Okay. We can see here actually that constant K1 increases up to some value of real power output and then starts decreasing. Okay. Then for reactive power Q equal to 0.5. Okay. Now, here when I say Q is positive, means we are supplying lagging power factor load. Okay. Therefore, for Q equal to 0.5, right, the constant K1 is varying in this fashion. Again, its variation is similar to what we got for Q equal to 0. It increases and it becomes maximum and then starts decreasing. You can see here actually that the value of K1 is less for Q equal to 0.5 as compared to what we got for Q equal to 0. Okay. Another graph which is shown here is that Q equal to minus 0.5, that is, it supplies leading power factor load. Okay. Now, we can see here that again K1 first increases and then starts decreasing. Okay. Therefore, the trend is similar, and one thing we observe that in this complete range where P is varied from 0.2 to 1 per unit, right, the K1 remains constant. I am sorry, K1 remains positive, not constant. K1 remains positive, and its magnitude is affected by the reactive power which it supplies. This graph shows the plot of constant K2 as function of P, that is the real power output of the generator, for 3 different values of q, right. Now, we find here actually that in all the 3 cases where q equal to 0, q equal to 0.5 or q equal to minus 0.5, right, the K 2 is increasing over the range which we have considered from 0.2 to 1. That is, these computations have been done or the graphs are plotted for varying real power output from very low value, that is 0.2 per unit to 1 per unit, right. And further we can see here again that as the reactive power output becomes negative, the value of K 2 is in more, that is K 2 is more for leading power factor load, and it decreases when the power factor is lagging, right. This constant K 3, if you see that it is also affected by the reactive power output q equal to 0. This is the graph, q equal to minus 0.5, this is the graph, and q equal to 0.5, this is the graph. But for a given value of q, the variation in K 3 as the value of p varies is very insignificant. Okay. This practically it is a flat curve. Now, this graph shows the variation of constant K 4 as function of real power output P for 3 different values of q. Again, there is q equal to 0, q equal to 0.5 and q equal to minus 0.5. Again, you can see here actually that the constant K 4 varies as the real power output varies and is also heavily dependent upon the value of reactive power output. But still we can see here actually that this constants K 1 to K 4, right, over the complete operating range which we have considered, that is real power output varying from very low value like 0.2 per unit to 1 per unit, and the reactive power varying from 0.5 to minus 0.5, right. The constant K 1 to K 4 remain positive all through. Now, here is the plot for constant K 5 again as function of real power P for 3 different values of q. Now, this line represents the reference axis, that is K 5 is 0, right. Now, you can see here actually that if I consider q equal to 0, right, in this particular case the value of K 5 is negative all through from 0.2 to 1 per unit value of P, that is the real power P is varying from 0.2 to 1. For q equal to 0, it is all through. Then when it is plotted for q equal to 0.5, right, it is seen that for P varying from 0.2 to some value around 0.35 or so, right, the K 5 is positive and then it becomes negative. Similarly, for q equal to minus 0.5, K 5 remains positive for about for P equal to 0.5 nearly, and then it becomes again negative. Therefore, this K 5 is the most important parameter, right, which affects the small signal stability of the system, and sometimes we call this K 5 as the culprit. Now, we can very clearly see actually in this plot that K 5 is positive for light loading condition, right, while it becomes negative for heavy loading conditions. But even actually in this particular case we find actually that the for a moderate loading also it is negative. And once this K5 is negative, right, it produces a negative damping torque coefficient when the AVR gain is increased. The last plot is for the constant K6, which shows actually the variation of constant K6 as function of P for 3 different values of Q equal to 0, Q equal to minus 0.5 and Q equal to 0.5. Again we can see here actually that yes, the constant K6 is positive all through, right, and it decreases as the real power output P increases for any value of Q. That is, you can see that Q equal to 0.5 or Q equal to 0 or Q equal to minus 0.5, it decreases. But we can clearly see actually that the value of K6 remains positive. Okay. Now, to understand more clearly the effect of K5 on damping and synchronizing torque coefficients, the computations were carried out for synchronizing torque coefficient as a function of Ka, that is the AVR gain. Now, we have considered two loading conditions. One loading condition is corresponding to one loading condition is such that K5 comes out to be positive. Therefore, this, that is K5 equal to 0.0309, where the real power output is 0.4 per unit and reactive power output is 0. It means it is a light loading condition, K5 is positive. Now, when we increase this AVR gain, then synchronizing torque coefficient, this is the synchronizing torque coefficient, it decreases, right. Although it is positive all through, it decreases, its magnitude decreases. For the same operating condition, the damping torque coefficient is plotted here, and it is seen actually that the damping torque coefficient increases with increase in K, and it becomes maximum for some value of K, then it starts further decreasing. Now, over this wide range of K, that is in this graph, the K is varied from 0 to 500, right. Now, over this complete range, we can clearly see that the Ks is positive, but it decreases. However, the Kd, that is the damping torque coefficient, it increases and then starts decreasing, but still it is positive all through over the complete operating range, that is K varying from 0 to 500. Then we have considered another loading condition, a heavy loading condition. The loading condition is that real power output P is 0.9 per unit and the reactive power output is 0.3 per unit. For this operating condition and other system parameters, okay, the K5 is computed, it comes out to be minus 0.1475. Now, considering this K5 equal to minus 0.1475, okay, and all other constants which were computed for this operating condition, right, the value of K synchronizing torque coefficient and damping torque coefficients are computed. The synchronizing torque coefficient, you can see here, it increases with the increase in AVR gain Ka, right. It, you know, the over a small range practically it is constant, but afterwards it increases and it is positive all through. Okay. Now, this graph shows the variation of damping torque coefficient Kd. Okay. you can easily see that when Ka is 0, the value of Kd is slightly positive. We have seen actually in the previous discussion, right. If we do not include the AVR, okay, and assume constant field voltage, right, and at that time the effect of demagnetization or armature reaction is to give some positive damping torque. Therefore, K equal to 0 is small positive damping torque, and as the value of K is increased, the damping torque becomes 0, right, and then it remains negative. It becomes it attains some maximum negative value, and then it decreases. Okay. And we can see here actually that although it is positive initially, K equal to 0, then it decreases at a fast rate, it becomes negative, right, and over the range 0 to 500 the Kd is negative all through, right. It means we find here that the when you include the AVR, then the damping torque becomes negative. Okay. Now, in any practical system, automatic voltage regulator is required to regulate the terminal voltage, okay, because we cannot say that we will go for a manual excitation control and keep this field voltage constant. If you do that, you would find actually that the negative damping torque is not produced, but AVR is required. And further, to regulate the terminal voltage within this certain tolerance, right, you have to have certain steady state gain. Larger the value of AVR gain, right, less will be the steady state error. Okay. And therefore, AVR is required to regulate the terminal voltage. It has to have large gain, because larger the gain of the AVR, right, its response is going to be fast, and the excitation system whose response is fast is capable of improving the tangent stability limit of the system. However, when we consider the small signal stability or dynamic stability of the system, right, we find that it will add negative damping torque coefficient or negative damping torque. Now, when the system has negative damping torque, whenever the oscillations are created in the system, these oscillations will grow. Okay. And when the oscillations grow, you will find actually that on any power transmission line, you will find actually that due to the rotor oscillations, right, there will be oscillations in the power flow on transmission lines, right, and the protective relays are provided to detect these oscillations, and protective relays will disconnect the system or trip the transmission line whenever such oscillations are produced before the system loses synchronism, right. But the problem basically is that can we allow this situation to happen? Answer is obviously that yes, we have to find a solution to overcome this problem of negative damping produced due to the AVR action, and the answer is the incorporation of power system stabilizer, right. Now, first let us see what is the function of the power system stabilizer. Here I have written basic function of power system stabilizer. We have to very clearly understand the basic function, then we will try to see how we achieve this objective. Power system stabilizers add damping to electromechanical oscillations. It is a fundamental thing that we are talking of electromechanical oscillations, that is the oscillations of the synchronous machine rotors, right. This is the electromechanical oscillations. essentially the power system stabilizer act through the generator's excitation system in such a way that a component of electrical torque proportional to speed change is generated. That is, we can see here the PSS act through the generator's excitation system. That is, when I discuss the different type of excitation system, at the AVR input, I have repeatedly told that there is one signal coming from the power system stabilizer, okay? And that signal was denoted as Vs, a stabilizing signal, right. Therefore, we can say here that this acts through the generator excitation system, and it acts in such a way that a component of electrical torque proportional to speed change is generated. We know that a torque which is produced in phase with the speed deviation, right, is the damping torque. The damping torque is Kd into delta omega r, right. Therefore, if we can produce a torque which is in phase with speed deviation, then it will be then it acts as a, or it acts to damp the oscillations. Now, we can further say that this torque which is produced is the additional, this is an additional, in addition to the damping torque, because system has its own damping also. There is always some damping which is there inherent in the system. Therefore, the PSS will provide a damping torque which will be additional to the existing system damping. A power system stabilizer is used to add a modulation signal to the generator's AVR reference input. That is, the stabilizing signal which we obtain through the power system stabilizer, right. That signal will be added at the summing point of the AVR, or we can say actually that it is added to the AVR reference input. Okay. Now, let us again come back to our K1 K6 model, that is the Halpern-Phillips model. Now, in this model, let us see how to incorporate the PSS. Now, this is the summing point, where the reference voltage is compared with the terminal voltage. In the AVR, we have this is a small signal, or you can say the small perturbation model. Therefore, all the quantities are shown as deviations from the nominal values, right. Delta V reference is the deviation from the reference of voltage. Okay. Then this signal delta V1 is corresponding to delta ET, because this transfer function was incorporated to take account for voltage transducer. Okay. Therefore, at this summing point we want to add a signal. This signal we are representing as Vs, and this will be added. We are putting a plus sign here, right. Now, this signal is derived from the speed deviation, that is in this transfer function model. This is the point where I can sense the speed deviation delta omega r. Okay. Therefore, here I put a transfer function. We will denote this as GPSS, that is the transfer function of the power system stabilizer. its input is derived from the speed deviation. Okay. The output of this transfer function, that is the will be the stabilizing signal, and this stabilizing signal is added to the summing point of the AVR. Okay. That is, you can see here actually in this block diagram, what I have done is I have taken input from this point which represents delta omega r. Okay. It enters the transfer function of the PSS, and output of the transfer function of PSS is the stabilizing signal. This stabilizing signal is put here at the summing point. Okay. Now we have to see actually that in practice how do we physically realize the speed deviation signal, because you can sense the speed by putting a speed transducer on the shaft of the synchronous generator. That is, generally today the standard practice is to have a toothed wheel mounted on the shaft of the synchronous generator, and we put a magnetic pickup, right. Therefore, the number of pulses which are generated by the magnetic pickup are proportional to the speed of the shaft, right. And we can very precisely measure the actual speed of the synchronous generator, and this speed is compared to the reference speed, and the difference is the delta omega, the speed deviation. Okay. And now what we have to see is that what should be the structure of this GPSS, what should be the transfer function of the power system stabilizer. Now, to understand this, what we do is we look at this transfer function model carefully. Now, you can see here actually that when this signal Vs is injected here, okay, let us see that we want to obtain a air gap torque or variation in air gap torque by varying this Vs. Okay. Suppose actually I am just putting signal, stabilizing signal Vs, and I want to know how much is the air gap torque produced due to this signal only. That is, you want to know how much is the air gap torque produced by this stabilizing signal only. Now, you can easily see that the signal or the air gap torque produced can be easily obtained through this loop. Can you see this? This is the loop actually, because here we are not going to consider the deviation in angle, that we are looking only that if I am putting this signal, how much is the stabilizing signal produced. Therefore, you have to see very carefully here let us just look actually that how much is the delta psi FD produced due to Vs. Okay. Then the torque produced due to the PSS will be equal to delta psi FD into K2. This is the torque which is going to be produced. Okay. And therefore, we can say that if we can write the expression for delta psi FD as a function of Vs, right, then we can make out actually that if I vary this Vs, how much is the stabilizing torque produced. Okay. Now, you can see that if this Vs is coming here, right. Now, to find out this delta psi FD due to this stabilizing signal only, we have to consider only this portion of the transfer function. Okay. Now, delta psi FD can be written, now if I just see it here, we can write down looking at this expression delta psi FD equal to this transfer function, that is you put k 3 over 1 plus s times t 3. Okay. Now, input to this is coming through this g e x s, and we will be assuming g e x s as k, right. Therefore, this is coming through k a. Okay. And now, input to this is V s minus delta V 1, V s minus delta V 1, we are assuming delta V reference to be 0. Okay. Therefore, we can put k, you can take this k into V s minus, further to simplify this understanding we will assume this T r equal to 0. This time constant of the voltage sensor or voltage transducer is very small, and you can make this T r to be 0. So, that we can say that here it is V s minus k 6 times delta psi f d. Okay. That is, we get one simple expression, this multiplied by V s, that is this delta psi f d. I can write now here delta psi f d produced due to stabilizing signal only can be written as k 3 divided by 1 plus s times t 3 multiplied by k a into V s minus k 6 delta. Okay. Now, this expression which I have written here is simplified and put in this form, delta psi f d equal to k 3 k 1 plus s times t 3 in bracket minus k 6 delta psi f d plus V s. Okay. This is a very important step, one should very carefully derive and see that the delta psi f d produced due to the stabilizing signal V s can be written in this form. Now, here now if you simplify this and write the expression for delta psi f d divided by V s, that is the transfer function relating the change in flux linkages due to stabilizing signal only, the delta psi f d upon V s, k 3 k divided by 1 plus k 3 k 6 k plus s times t 3. This is the simple transfer function you will get relating the change in flux linkage to stabilizing signal V s. Okay. Now, to have very clear understanding, okay, about this effect of stabilizing signal on the air gap torque produced due to stabilizing signal, we take this example. For a typical example which we considered earlier, these were the constants k 1, k 2, k 3, k 4, t 3, k 5 was taken as negative, k 6 is taken as 0.3. This T r is neglected, although in the previous case we have taken T r equal to 0.02, but for the purpose of simplification we are ignoring or we are neglecting this T r, making T r equal to 0. The effect of neglecting T r is or I can say that the error caused due to this assumption is practically insignificant. We will assume this G E x, the transfer function of the exciter, as K A, and its value we will take as 200, a typical value equal to 200. Okay. Now, with this parameters assumed, if we make the compute this ratio delta psi f d divided by V s, it comes out to be equal to 66.66 divided by 21 plus 1.91 s. Okay. Now, you assume that the rotor oscillation frequency is 10 radians per second, 10 electrical radians per second. So, that put S equal to J 10. Then this transfer function becomes 66.6 divided by 21 plus J times 19.1. It was 1.91, omega is 10, it becomes 19.1. Now, we can write down the delta T PSS, that is the air gap torque produced due to the PSS action only is written as, can be written as delta T due to PSS. That is delta T PSS is delta T or air gap torque due to PSS, which is going to be equal to K 2 times delta psi f d due to PSS. Okay. Now, we have just now computed actually this delta psi f d, okay, as the transfer function delta psi f d by V s. Okay. Therefore, now you substitute the expression for or the value for T K 2, right. We get the delta T due to PSS as 1.5 into 66.6 divided by 21 plus J times 19.1 into V s, into V s. Now, for this complex you can say the function, right, we can find out its magnitude and phase angle. We can find out the magnitude and phase angle. That is what you have to do is you take magnitude of the numerator divided by magnitude of denominator, and this ratio will give the magnitude. Then find out the phase angle of the numerator. In this case, phase angle of the numerator is 0 because it is a real number. Find out the phase angle of the denominator. For example, in this case, phase angle of this denominator term is going to be, say theta is the phase angle, is tangent inverse 19.1 divided by 21. Okay. And therefore, the net phase angle of this function will come out to be negative, right. Therefore, delta T PSS is obtained as 3.522, its phase angle is minus 43.3 degrees into V s. Okay. Now, suppose I want that this the torque produced due to PSS is a pure damping torque, Okay. In that sense that I must produce this V s, the stabilizing signal, it should be such that it will compensate for this phase lag, okay. And therefore, if I now assume the transfer function, I am just putting very high, very you can say a simple case, that is if I assume GPSS equal to, I am just putting GPSS equal to some constant, I call it K a K stabilizer, K A S T, K gain due to stabilizer, okay. And its phase angle I make it 43.3 degrees. Okay. Then delta P, delta T PSS can be written as 3.522 Ka stabilizer I think you can put the STAB, stabilizer. Sometimes we use the word K, stabilizer only, not A can be deleted here, into delta omega r, because Vs is equal to, what is Vs? Vs is equal to GPSS into delta omega r. Therefore, if I now assume actually that the GPS is equal to a constant and having its phase angle equal to 43.3, right, then the air gap torque produced due to PSS is 3.522 into K stabilizing delta omega. Okay. Now, if you we can write the same thing which I have written just now as delta T PSS is equal to gain of PSS at omega equal to 10 into 3.522 into delta omega. This is what we have written. Now, we will try to write down this damping torque coefficient due to PSS. Kd due to PSS will be equal to gain of PSS into 3.522, because this torque is purely a damping torque, right, and we have compensated for the phase lag which is produced by choosing the appropriate transfer function of PSS. So, that we can say the damping torque produced due to PSS is equal to the gain of PSS, whatsoever gain you put, into 3.522, and the net damping torque which is going to be produced will be equal to Kd due to AVR action plus Kd due to PSS. The net damping torque which is going to be produced will be Kd due to AVR action plus Kd due to PSS, plus there will be some inherent damping torque which may be present in the system, because we have seen actually that when I did not consider the AVR, we did not consider the PSS, still there was some damping torque produced, a positive damping torque due to demagnetization effect. Okay. Now, suppose I want actually that I want to simply nullify the effect of AVR action, right, then the Kd PSS should be equal to the Kd due to AVR action, that is negative. For example, in the problem which we had taken earlier, we found that Kd was found to be minus 12.27, when we have considered only the effect of field flux changes, that is the demagnetization effect or armature reaction effect, right. We found actually that the damping torque contributed, I am sorry, not it was due to the AVR action with Ka equal to 200. The damping torque contributed is minus 12.27, right. Therefore, now if I take the PSS gain, if I take PSS gain equal to 12.27 divided by 3.522, right, then this PSS is going to produce a positive synchronizing torque coefficient which will just nullify the negative damping torque produced due to the AVR action, right. But now if I take gain, which is more than this, that is if you set the PSS, so its gain is more than this ratio, that is 12.27 divided by 3.522, right, then it is going to add to additional damping. It will provide additional damping torque, right. And therefore, we come to one very important conclusion, that the that the PSS which we have to provide should be in a position to compensate for this phase lag, and it should have certain gain so that it can provide additional damping. Okay? Because the damping due to demagnetization effect was very small, although it was positive when we assumed this the manual control, right. There was some positive damping, but that was very small, and therefore, actually we want certain damping which will quickly damp out the oscillations whenever they are produced, right. And therefore, there is a necessity to design the PSS properly. Now, another one point which we have to understand is that suppose I provide PSS which will not fully compensate for this time for this phase lag, because here the phase angle is 43.3 lagging, and if I make PSS to have phase lag less than 43.3, that is the PSS compensates for an angle which is less than this, that is I can take instead of 43.3 degrees, let us take 30 degrees, right. Now, this situation is known as the undercompensation, that is we are not fully compensating the phase lag which is there between the stabilizing signal and the air gap torque. Okay. Now, if you have this situation, what will happen? If you look at the let us look at a plane here. I denote this as a delta delta, and delta omega r is along y axis. Okay. If suppose you fully compensate for the phase lag by choosing the PSS parameters, right, then the delta T PSS, delta T due to PSS will be along this axis, right, and this is a pure damping torque. Okay. Now, suppose you instead of fully compensating, if you do undercompensation, right, in that case this is your delta delta, this is your delta omega r, delta T PSS will lie somewhere here, delta T PSS will be in this position. Okay, you understand this point? Because we have partially compensated for the system phase lag. Now, if this is the situation, then this torque can be, or this delta T PSS can be resolved into two components, one along delta omega r, another along delta delta, right. Now, what we see is that this component, this is the component of delta PSS along delta delta. What is this component known as? Synchronizing torque, and this component is the damping torque. Therefore, the moment you have a situation where you have undercompensated, right, we get some additional synchronizing torque, right, and it is desirable, because we know that whenever you design a system, we should have synchronizing as well as the damping torque coefficient to be positive, and here we add. Now, you take a third case where if you overcompensate for this, suppose you overcompensate, that is instead of having the phase angle of the GPSS exactly equal to the phase lag of the system, then the delta T PSS produced can be shown in this plane. It will come in this second quadrant, that you can put delta T into PSS. And now you can see here actually that if we resolve this into two components, we get a component in phase with delta omega r, which is the damping torque, and we get another component which is in phase with delta delta synchronizing torque coefficient, but now we get a negative synchronizing torque coefficient, right. And therefore, in practice it is necessary to design the PSS in such a fashion so that we do not overcompensate. Okay. Under compensation, if it is there is no harm. The literature shows that one can go for under compensation as much as 10 degrees to 30 degrees. Under compensation of the order of 10 degrees to 30 degrees. Now, what we have considered till now is a simple situation where the excitation system was represented by a constant gain K A only, right. Now, this representation is applicable to static excitation system, right, where the time constant of the exciter is very, very low. However, when we consider other excitation systems, right, then we have to account for the actual transfer function of the excitation system. And further we can see two important points, that the phase lag which is produced depends upon the operating condition, because it is function of the system constants, and the constants are function of operating condition. Okay. And it also depends upon the type of excitation system which we have considered, right. Therefore, from that point of view, the transfer function which we have to assume for the GPSS, or I am sorry, transfer function of the power system stabilizer, okay, will not be a very simple one. A general form of the transfer function block diagram of delta omega PSS is shown here. Without emphasizing, I have told you that the input signal to the PSS is the speed deviation, okay. And since we want to produce a torque in phase with the speed deviation, therefore, this is the most suitable input signal to PSS, and this signal is delta omega. Therefore, in the literature, this type of power system stabilizer, the power system stabilizer with speed deviation as input signal is known as delta omega PSS. This is delta omega, right. Therefore, we use this terminology. Now, here the general transfer function of PSS is shown here, that is input to this is delta omega, output is the stabilizing signal. Therefore, here first block is showing the stabilizer gain, The second block shows what is called wash out. This is a wash out block, wash out. And these two transfer functions represent the phase compensator, We have seen the function of this gain, how much gain is to be provided, because the gain will determine the amount of damping which is going to be produced. We have also seen the role of this phase compensator, because this phase compensator is to provide the required phase compensation, that is the phase lag of the system is to be compensated by putting phase lead. Therefore, compensator is to provide the desired phase lead for a given frequency. Okay. Now, the function of this washout, we will just understand why we require the washout block. Now, we want actually this stabilizing signal to be present only when the rotor is oscillating or there are oscillations in the system. Suppose there is a steady state deviation in the speed from the rated speed to some other value, there is a steady state deviation, right. During the steady state deviation, we do not want any stabilizing signal to be produced, because our basic function is to provide damping to the rotor oscillations. Okay. And therefore, we provide here a transfer function whose gain is going to be 0 when the frequency of oscillation is 0. That, for example, in case S T W or 1 plus S times T W, that if I put S equal to 0, then this transfer function provides the 0 gain, and when there is a steady state change in delta omega, no stabilizing signal is produced. Now, suppose you provide stabilizing signal or allow this stabilizing signal to be there, under steady state deviation, then it is going to unnecessarily affect our terminal voltage, because this signal is entering at the summing point of the AVR. We do not want actually the stabilizing signal to affect the terminal voltage also. Okay. This transfer function should be a high pass filter. Okay. Now, I will just sum up what we have discussed today. We have studied the effect of variation of loading condition on different constants, and we have also studied the how the PSH is to be incorporated to obtain the required positive damping. Thank you.